Let's talk about the differences between local and global interpolation methods in numerical methods, or any course where interpolation is taught. In our past few videos, we were talking about various interpolation methods. We have covered methods such as Lagrange interpolation and Newton's divided difference interpolation, which are both considered global interpolation methods, which I will talk about more here shortly. Also recall that we wanted to learn about interpolation methods as we want the ability to construct smooth, continuous functions such that we can find the output of our system for any given input. So, broadly, we can describe our interpolation process as we give some data, we fit an interpolating function given that it is both smooth and continuous, then assuming a good interpolation fit, we can plug any input within our bounds of our applied dataset to find the output. Now we are ready to begin talking about global versus local interpolation methods. Let's begin with global interpolation methods, as we have already seen a couple of these. The key difference between global versus local interpolation methods is the amount of our dataset that we are going to use to find the interpolating polynomial. A global interpolation method is going to use all possible data points to find its interpolating polynomial, whereas a local interpolation method is just going to use a subset of that total data. An example of a local interpolation method is spline interpolation, which will be talked about over the next couple of videos. So if you can imagine this table here with all of our possible data points contained within it, this is the only data we can use when creating a global interpolating polynomial. Meaning, no matter what method we use, be that Lagrange interpolation, Newton's divided difference, or something else, we are going to get the exact same global interpolating polynomial. Whereas a local interpolation method can use pretty much any subset of this data that we choose. For example, we could use any of these subsets to find a local interpolating polynomial. That should give us a good output approximation for any input in the range that we find our polynomials fit for. Therefore, you can think of a local interpolation method as finding many different small order polynomials, whereas a global interpolation method will often result in a very high order polynomial, as all data points must be implemented into our interpolation polynomial. So, let's go through a quick example of why local interpolation methods are helpful. Let's say that we were just given the data for temperature every day throughout the year last year, and we are asked to make a prediction for the second week of July this year. Well, creating one global interpolation with a polynomial of order 364 is a bit of overkill. Therefore, we would just use a local interpolating polynomial. In summary, we can say that often local interpolation methods are better at capturing and evaluating small subsets of our larger chunk of data. So, essentially, a more focused, less error-prone interpolating polynomial. Whereas global interpolation methods will give us a fit of very high-order polynomial that will tell us the trend of our whole dataset. But this can be prone to certain errors and more calculation time. However, they are extremely useful, particularly with data that follows a trend. In the past few videos, we have been talking about various interpolation methods. We covered methods such as Lagrange interpolation and Newton's divided difference interpolation. Also recall that we learn about these interpolation methods as we want the ability to construct smooth, continuous functions such that we can find the outputs of the systems wherever we wish, regardless of the information given to us. Now, let's talk about a new interpolation method called spline interpolation. If you recall, in the past interpolation methods, we constructed a polynomial from all of our discrete data points that we were given, and we made what is called a global polynomial interpolating function. By global, I mean that we used all of our dataset, and not simply a section of it, to develop the interpolating polynomial. Therefore, as I've previously mentioned, it doesn't matter if we use Lagrange interpolation or Newton's divided difference interpolation. Both methods will result in the same global interpolating polynomial as they take in and output the same result. Although great in some scenarios, sometimes using a global interpolating method isn't practical, or less efficient than simply taking a local interpolation. Why though? Well, as we add more data points to a global interpolating polynomial, we need to increase the polynomial order, which in certain applications can give wildly inaccurate answers, like this graph here for example. Therefore, it is going to be beneficial to us that we now have a local interpolation method. So, let's talk more about what local interpolation is and what that means. A local interpolation method means that we are only going to be interpolating between a subsection of data inputs rather than the whole of the dataset. Which basically means that instead of having one very high order polynomial that fits through all of our dataset, we're going to have several much lower order polynomials to fit a continuous function through interpolation. Let's now talk about what spline interpolation is and how it works. In the coming videos, we will get more into using and solving problems with various degrees of spline interpolation, but for now, let's talk about the various types of spline interpolation that we can have, and what they look like to give you a broad idea before getting into the details and examples about those methods. In this course, I will be covering first and second order splines, but just note that there are higher order splines that will just not be covered in this course. Firstly, the simplest spline that we can have is one in which all our data points connect by straight lines to their neighbors. This is called a first order spline, or also known as a linear spline interpolation, as all of our splines are, well, linear. Obviously, this is not quite smooth as we have these sharp-ish corners at our nodes. Therefore, more commonly, we use what are called cubic splines, or second-order splines, as they allow for both smooth and continuous functions that could look many different ways, such as the following. Like I said, in the coming videos, we will explore first and second-order splines more and talk about the theory and give some examples. Hey everyone, let's talk about what linear spline interpolation is and how we go about using it. Firstly, what is linear spline interpolation? In the past video, we talked about what spline interpolation is. So if you missed that video, check out the link in the description down below. In linear spline interpolation, we use the assumption that between our data points of interest, our system is linear. This means that we can connect our data points directly through straight lines, which, if you remember, is a first-order polynomial. Or, if we wish to interpolate between multiple data points, it is a series of segmented straight lines that might look something like this. As you can see, we usually get these unwanted sharp changes in our function, and you may see these called knots. These are unideal and why cubic splines are much more commonly used. However, these will be the subject of our next numerical methods theory video. So, now that we have an idea of what linear spline interpolation looks like, how do we go about actually finding an interpolating function such that we can find an output along this line here? Well, in a linear spline interpolation function, we have a piecewise function, where each linear spline is a simple straight line equation with the domain of the bounding data points. So, for example, if we wanted to define a linear spline for the following three subset of data points, we would have the following. Therefore, we can say that any general linear spline interpolation between 2 points can be written as the following, which is simply the equation of a straight line, where this term here is simply our slope, m. In the coming videos, we will complete a few example videos on linear spline interpolation. I hope that this video helped your understanding of the theory behind linear spline interpolation and how we go about using it. Hey everyone, in this video, we're going to be walking through a linear spline interpolation example. If you missed our previous video on the theory of linear spline interpolation, I will leave a link in the description down below for you. Let's get right into our questions. The first question here states that we first need to find our necessary interpolating functions, and then we are given a few inputs that we must find the outputs for. Let's first begin by plotting our points of interest around the areas in which we need to interpolate. In this example, we do not need to plot the 20 data point, as we already have one data point to the right of our largest point that we will be interpolating for. That is our 12 data point. So, we can see by this graph here that we need two interpolating polynomial functions, and our data point at 7 is actually unnecessary. So, as we talked about in the theory video, this is one of the major differences between spline interpolation and the global interpolation methods that we talked about. Spline interpolation does not need to use all the data points supplied to us, whereas methods like the divided difference and Lagrange polynomials do. Now, we can begin solving for our first and second interpolating polynomials for this question. Just briefly, since we are going to be finding straight lines or first-order polynomials as p1 and p2, let's just write out the equation for a straight line and a general first-order polynomial, and you can see that they are actually the same thing. We are now ready to begin solving for our two polynomials. To do so, we just need to apply the correct data points as our parameters for the general equation of a straight line and simplify. This results in p1 being 1.2x plus 0.8, with a domain of this function being the following. Secondly, we will now solve p2 in the exact same way using our data points at x equals 9 and 12. After applying our known values and simplifying, we are left with 4x over 3 minus 2 with a domain of 9 to 12. Now, we have our interpolating functions. We just need to apply our desired inputs. Firstly, we have x equals 2, and since that is in our domain of p1, that is a function that we will use. And you can see that this results in an output of 3.2. Secondly, we have x equals 5, which again falls in the domain of p1. Therefore, for an input of 5, we get an output of 6.8. Lastly, we have x equals 10, and this falls in the domain of our second interpolating polynomial function, p2. Applying an input of 10, we get an output of 11.33. And there we go. We just answered all the questions that we were asked. Hey everyone, let's talk about the theory of quadratic spline interpolation. Firstly, what is quadratic spline interpolation? As the name implies, quadratic spline interpolation is a specific type of spline interpolation that uses quadratic equations as our splines. If you recall, in the past video, we talked about what spline interpolation are, so if you missed that video, check out the link in the description down below. Briefly, splines are an interpolation method that allow us to fit smaller polynomials to a subset of our given data. In this diagram here, we are given the white data points, and the blue line drawn symbolizes the quadratic interpolating polynomial that we will learn how to find here shortly. A major benefit of spline interpolation over alternative interpolation methods is the flexibility that it provides us. For example, with global interpolation methods, such as Newton's divided difference interpolation, we must use all possible data points supplied to us, which can create very high-order polynomials, whereas spline interpolation can use only a subset of our total data, and is known as a local interpolation method because of this. Meaning we're only going to be using very small order polynomials versus large order polynomials that commonly arise with divided difference or Lagrange polynomials, which in some scenarios can provide problems or unnecessary complexity. As an example, let's imagine that we have a very large dataset of let's say 1,000 points, and we simply want to interpolate a few points between let's say points 38 and 40. Using divided difference interpolation here will result in an extremely high order polynomial, which is a bit of overkill for what we are trying to accomplish. This is an example where some form of spline interpolation can shine. And in this video in particular, we're talking about quadratic splines. In the past video, we talked about linear splines. However, as we learned, these are much less used in much of numerical analysis, and they result in non-smooth curves at data points. Quadratic splines, and particularly cubic splines, are much more common as they introduce curvature, which, as you can see by the following example, is often very important to reduce errors of our interpolating functions. Essentially, with quadratic spline interpolation, we're going to be increasing our interpolating polynomials function's order by 1. Instead of using first-order polynomials to find our interpolating functions, we're now going to be using second-order polynomials. In terms of our data points, that will look something like this. But how do we go about finding the quadratic interpolating function itself? Although we now have the added benefit of curvature to our splines, we also have a bit more complexity in finding our spline functions. Whereas previously we simply were using the equation of a straight line to solve for our splines, we can no longer do that. Looking at the general equation for a second-order polynomial, it is clear that every spline we create, we are going to have 3 unknowns. These being the coefficients for all of our x variables, so x squared and x, and then another one for our constant. And these are commonly denoted as a, b, and c, as you can see here. So, how do we go about finding 3n worth of equations? Well, we need to find them by being clever and understanding our system more. Firstly, we know that at every x data point we are given, we know the y value associated with it. So, for example, if we plug either x1 and x2 into p1 of x, well, we know we are going to get y1 and y2 back respectively. And there is 2 equations right there. Similarly, this is true for p2 of x. Therefore, this gives us 2n worth of equations, as every spline is going to guarantee us 2 equations that we can use to solve. So, for our above example, this will give us 4 of our 6 equations that we need. Next, we can look at our interior data points, meaning our non-terminal data points. Isn't it true that if we wish to have a smooth function at every internal data point, our slopes will be equal where they connect? Therefore, at every internal point along our region of interpolation, we are going to be able to find n-1 equations, which would look something like this, in which you would plug in the above equations, take the derivative, and then solve. In our above example, this gives us 1 equation. Therefore, we are still missing 1. Here it is common practice to assume that the curvature of our first term is 0, meaning the second derivative of our first spline is 0, and thereby making our first polynomial a linear spline, but the remaining curves will have curvature. Hey everyone, in this video, we're going to be walking through a quadratic spline interpolation example. If you missed our previous video on the theory of quadratic interpolation, I will leave a link in the description down below for you. Our first question tells us that we need to find all the relevant interpolating functions between the following data using quadratic spline interpolation. The first thing that I'm going to do is go ahead and plot our data points so that we can better visualize what we are being asked to solve. Plotting the data that we were given looks like this. It is clear that there are going to be 3 splines that we are going to have to find, which makes sense as our number of splines, n, will always be 1 less than the number of data points that we are given. As we learned in our quadratic spline theory video, we are going to have 3n unknowns. Therefore, we are going to have 9 unknowns and therefore need 9 equations to find all of our necessary unknowns. Before we get into solving this problem, I'm just going to go ahead and develop a plan to find our solution. The first thing that we are going to do is write out our quadratic functions for all 3 of the interpolating polynomials that we wish to find. Secondly, we will identify our 9 unknowns within our functions so that you can visualize what we are going to be finding. Thirdly, we are going to be presented with a system of equations that we will solve and find all of our unknowns. Then, lastly, once we have our whole system solved, we just need to plug in our x inputs for the second part of the question. Let's begin solving. As we said, the first step that we are going to do is write out our interpolating polynomials. Using quadratic interpolation, each of these equations are simply second-order polynomials, which look like this. Our second step is to identify our 9 unknowns, which is simply all the coefficients, which I will highlight here. Now, we need to find our 9 independent equations to solve for our 9 unknowns. As we learned in the last video, we can get 2n equations through evaluating each of our 3 polynomials at our known data points. So let's just go ahead and do that. To elaborate a bit more, we're going to evaluate our first polynomial with its 2 data points, so x1 and x2. P2 will be evaluated at x2 and x3, and lastly, P3 will be evaluated at x3 and x4. As you can see, this results in our 6 equations, which I will highlight here in number. Secondly, again, as we learned in our quadratic interpolation theory video, we can find n-1 equations through the property of smoothness at our interior data points, which in this example will give us 2 more equations as we have 2 interior data points. To find these, we're going to evaluate the derivatives and evaluate them at their shared x value. Therefore, to get our first equation here, we are going to take the derivatives of p1 and p2 evaluated at x2. This works out to the following equation. Secondly, we will repeat this process for our second interior data point. Therefore, we will evaluate the derivative of p2 and p3 and evaluate them at x equals x3. And this results in the following equation. Now, as you can see, we have 8 equations. We are still missing an equation to solve for our 9 unknowns though. At this point, it is common to assume the first point's second derivative is equal to 0, and thereby assume that our first polynomial is actually linear interpolation, as the assumption assumes 0 curvature. However, if you're writing a test or just using quadratic interpolation, you may be given or assume a better assumption. If so, obviously use that and not this assumption. However, for me, in this example, this assumption is the best option. Therefore, our final equation works out to the following. Now that we have our 9 equations, we can solve for all 9 of our unknowns. To do this, we could try doing it manually. However, this would not be fun. We have all linear equations, and therefore, we have what is called a system of linear equations. Therefore, we can use one of our linear system of equation solvers that we developed previously. So, let's just write out a matrix so that we know what we are trying to solve. You can think of all these columns as our coefficient values for each of our equations. I will write that out here so you can better visualize it. Now, I'm going to use our Gauss elimination solver with partial pivoting that we developed in a previous numerical methods video. I will leave a link to that video down in the description down below. However, there are systems of linear equation solvers online that you can find by simply Googling them. Now that we are inside Python, I'm just going to take a minute and enter our matrix into 2 variables, as that is how I wrote this Gauss elimination solver function. Now, we just need to call our function and insert our variable matrix and then our constant matrix. And as you can see, we have now solved for the 9 unknowns. Each of these x values represents a coefficient for our 3 interpolating polynomials. x0 is a1, x1 is b1, x2 is c1, x3 is a2, and so on. Applying these 3 equations to our interpolating polynomials results in the following equations. To visualize these polynomials, I'm just going to plot them rather crudely inside Microsoft Excel. This results in the following graph, and as you can see, our first interpolating polynomial is a linear spline as we previously mentioned. Now, back on our blackboard, we can begin solving the second question that we were asked. We were asked to evaluate the interpolating polynomials at inputs of 2, 4, and 7. Quickly, I'm just going to write out our polynomials in their respective domains. For an input of 2, we're going to be using our first interpolating polynomial based on our domains. This results in an output of 2.5. Secondly, for an input of 4, that falls in the domain of our second interpolating polynomial. This results in an output of 4.75. Lastly, for an input of 7, we will use our third interpolating polynomial. This results in an output of 13.15, and we have now answered all the questions that we were asked. I hope this video helped your understanding of how we go about solving problems using quadratic spline interpolation. Hey everyone, in this video we're going to be talking about cubic spline interpolation theory. We're going to begin with a brief overview of spline interpolation, define what cubic spline interpolation is, speak about why it is used, and then lastly we'll walk through how to implement a cubic spline interpolation. Cubic spline interpolation is a powerful technique used to approximate a smooth curve that passes through a set of data points. Similar to the linear and quadratic splines that we have talked about in our past few videos, it breaks down the data range into smaller segments. However, we are now going to fit a cubic polynomial to each section. And this ensures continuity and smoothness at the connection points, which is something we were lacking in both the linear and quadratic splines. So, let's imagine that we have a system where we are tracking the amount of time that it takes to fill a bucket. As you can see, we are given 5 discrete data points, but we are interested in making a function that passes through all of our relevant data points. There are various types of spline interpolation, as we have talked about, including linear and quadratic. In brief, a linear spline interpolation simply connects our data points using straight lines, or a first-order spline, which, although simple, tends to lead to inaccurate interpolations as there is no curvature in our function. Secondly, a quadratic spline fits a second-order polynomial to our interpolation function, and this adds curvature to our interpolating function, but we only have 1 degree of freedom, which forces us to use parabolas and parabolas alone. Now we will talk about the most common type of spline interpolation, that being cubic spline interpolation. Unlike the quadratic splines, what makes cubic spline interpolation powerful is that it ensures continuity and smoothness at the connection points. This means that the curve and its derivative up to the second order are continuous throughout the entire range, whereas in quadratic spline interpolation, this is only true for the first derivative. Now, let's explore the benefits of using cubic spline interpolation. Firstly, it provides a more accurate representation of the data compared to simpler interpolation methods. The smoothness and continuity properties ensure that the interpolated curve captures the overall trend without excessive oscillations. So now that we have an idea of why cubic splines are useful, let's talk about how to use cubic splines. So, between each connection point, we are going to have a third-order polynomial, that being a cubic spline. So, imagining a set of data that looks like this, each point that we wish to interpolate through will be described as the following general cubic polynomial. Therefore, this will create a set of polynomial equations that look like this that we need to solve the coefficients for. And we will have n equations. Now all we need to do is develop a methodology for how we are going to solve for all of these unknowns. The first thing we need to do is determine how many unknowns we actually need to solve for. Well, as you can probably imagine, the number of unknowns that we need to solve for depends on the number of cubic splines that we are interpolating for. Therefore, we can say that for every spline n, we will have 4 n unknowns, meaning that we need to find 4 equations per spline that we add. Let's try to find our 4n equations. Firstly, we will have some known data points. These are the input-output pairs that we are interpolating through. Because each data point will share a spline, we actually get 2n equations. Therefore, we just need to find 2n more equations to be able to begin solving our system of equations. For our intermediate data points, we can define continuity and say that the first derivatives need to be equal. This statement will be true at every interior data point that we have, and this will give us n-1 equations. Therefore, we are missing n-1 equations still. Likewise, we know that we actually want our interior data points to also have equal second derivatives, as we want our splines to be as smooth as possible. Therefore, this is going to be another n-1 equations. This leaves us with -2 equations. We have some options at this point. However, the most common way to find these two missing equations is through making some assumptions about the endpoints of our piecewise spline function, much like we did for the quadratic spline interpolation. The first common approach is a natural cubic spline, which ensures that the curve is continuous and has 0 second derivatives at the endpoints of each interval. Therefore, we get two equations by setting our first and last data points' second derivatives to 0. Whereas a clamped cubic spline requires some extra data. We specify the slopes, the rate of change of the curve at the first and last data point. These slopes are called the clamped conditions. By providing these clamped conditions, we ensure that the curve has the desired slope at the endpoints, which can be helpful when we have prior knowledge or constraints about the behavior of our curve. It is worth noting that these are not the only two ways we can find our missing equations. They are just the most common. Other variations do exist, but they'll find two equations through playing with various boundary conditions and constraints. Lastly, all you need to do is solve your system of linear equations, which we have talked about plenty in the past. Hey everyone, in this video, we're going to be walking through a natural cubic spline interpolation example. If you missed our previous video on the theory of cubic spline interpolation, I will leave a link to that in the description down below for you. Before we jump into this example, let's quickly recap what cubic spline interpolation is. Cubic spline interpolation is a mathematical technique used to approximate a smooth curve passing through a given set of points. It's especially useful in situations where we have scattered data points and we want to create a continuous curve that captures a general trend. We can then use that curve to find valuable information about our data. Alright, let's take a look at our example. Here we have a set of data points representing the growth of a plant over time. Our goal is to interpolate a smooth curve that accurately represents the growth pattern between these supplied discrete data points. As you can see, we have 4 data points, and our task is to find the natural cubic spline that passes through these points. As we learned in our cubic spline interpolation theory video, we know that we were always going to have one less spline than our number of supplied data points. Therefore, with 4 data points, we will have 3 splines to fit cubic functions to. We also learned that for each spline we need to find, denoted by n, we will need 4n equations, such that we can solve for our 4n missing coefficients. Therefore, we have 12 missing coefficients, as you can see here. So, let's quickly make a plan of attack on how we want to go about solving this problem. First, we need to find 12 equations such that we can solve for our 12 missing coefficients. Once we have the 12 equations, we will plug them into a linear system of equations solver and then be complete with this problem. But stay with me and we'll walk through this problem fully together. So, let's begin working out how to find our 12 equations. As we learned in the previous theory video, we can get 2n equations through evaluating each of the 3 polynomial functions at our known data points. So let's just go ahead and do that. All we're doing here is plugging in our x values at our known points and simplifying. But to elaborate a bit more, we're going to evaluate our first polynomial with its 2 data points, so x1 and x2. P2 will be evaluated at x2 and x3, and lastly, P3 will be evaluated at x3 and x4. As you can see, when we are done here, this results in 6 of our 12 equations. Secondly, as we learned in the cubic spline interpolation video, we can find n-1 equations through the property of smoothness at our first derivatives of our interior data points, which in this example will give us 2 more equations as we have 2 interior data points, and you can see that here. Again, like we just previously did, we can do the same thing with second derivatives as we know we have continuity there as well. And this will also give us n-1 equations. To get the first equation here, we are going to take the derivative of our previously calculated first derivative of p1 and p2. Then we are going to equate them and plug in our x value where the continuity is occurring, which is x equals 3. This works out to the following equation, and I'm just going to rearrange it, such that all variables are on one side and the constant on the other side. Secondly, we can repeat this process with our second interior data point, between p2 and p3. Therefore, we will again take the derivative of our first derivative p2 and p3 functions we found earlier and evaluate them at x equals x3, which is 5. And again, we will rearrange this equation to put all variables on one side and just leave our constant, which is 0, on the other side of the equation. Now, as you can see, we have 10 equations and we are only missing 2. We were told to assume a natural cubic spline, so let's do that. In a natural cubic spline, we assume that the second derivative of our endpoints are both equal to 0, meaning at that point it is simply a straight line. So let's just go ahead and calculate the second derivative of p1 and p3 at points x1 and x4 respectively to get our remaining 2 equations. And again, just ensure that we are always rearranging our equations to put all our variables on one side, and we'll leave our constant, which is a 0 in this case, on the other side of the equation. Now that we have all of our 12 equations, we can solve for our 12 unknowns. To do this, we could try doing it manually. However, this would not be fun and take a while. Through using simple polynomials, we will always have linear equations, and therefore we have a system of linear equations. And from our previous lessons in this course, we actually know how to solve these. So I'm just going to write out our matrix so that we know what we are trying to solve. You can think of all these columns here as our coefficient values for each of our equations. And I will write this out here so that it's easier to visualize. Now, I'm going to use our Gauss elimination solver with partial pivoting that we developed in a previous numerical methods video. I will leave a link to that video also in the description down below if you missed it. However, there are systems of linear equation solvers online that you can find by Googling them. Now that we're inside Python, I have opened the Gauss elimination system of equations solver with partial pivoting. I took a minute already and entered our square matrix we just wrote down and entered in our variables and constant matrices here. We just need to call our function and insert our variable matrix and then our constant matrix and run the program. And as you can see, we have now solved for our 12 unknowns. Each of these x values represents a coefficient of our 3 interpolating polynomials. x0 is a1, x1 is b1, x2 is c1, x3 is d1, and so on. To visualize these polynomials, I'm just going to plot them rather crudely inside of Microsoft Excel, keeping in mind our domains that we have talked about previously. As you can see, this results in the following very nice smooth function. Now, back to our blackboard, we can now solve the second question we are being asked. We were asked to evaluate the interpolating polynomials at inputs of 1.5, 4, and 7. Quickly, I'm just going to write out our polynomials and their respective domains. For an input of 1.5, we're going to be using our first interpolating polynomial based on our domains. This results in an output of 1.876, Secondly, for an input of 4, it falls on our second interpolating polynomial, which has an output of 5.9. Lastly, for our input of 7, we will use our third and final interpolating polynomial. This results in an output of 10.58, and we have now answered all the questions that we are being asked. Hey everyone, in this video, we're going to be walking through a clamped cubic spline interpolation example. If you missed our previous video on the theory of cubic spline interpolation, I will leave a link in the description down below for you. Before we jump into the example, let's quickly recap what cubic spline interpolation is. Cubic spline interpolation is a mathematical technique used to approximate a smooth curve passing through a given set of points. It's especially useful in situations where we have a scattered data set, and we want to create a continuous curve that captures a general trend. We can then use that curve to find valuable information about our underlying data. Alright, let's take a look at our example. Here we have a set of data points representing the growth of a plant over time. Our goal is to interpolate a smooth curve that accurately represents the growth pattern between these supplied discrete data points. As you can see, we have 4 data points, and our task is to find the clamped cubic spline that passes through these data points. And we are also told at our endpoints that we have a derivative of 4. As we learned in our cubic spline interpolation theory video, we know that we will always have one less spline than our supplied number of data points. Therefore, with 4 data points, we will have 3 splines to fit cubic functions to. We also learned that for each spline we need to find, denoted by n, we will need to find 4n equations such that we can solve for our 4n missing coefficients. Therefore, we have 12 missing coefficients as you can see here. So, let's quickly make a plan of attack on how we want to go about solving this problem. First, we are going to find 12 equations such that we can find our 12 missing coefficients. And to find them, we will plug our 12 equations into a linear system of equation solver and then complete the problem. But stay with me and we'll walk through this problem fully together. So, let's begin by trying to find our 12 equations. As we learned in the previous theory video, we can get 2n equations through evaluating each of our 3 polynomial functions at our known data points. So, let's just go ahead and do that. All we're doing here is simply plugging in our x values and simplifying. But to elaborate a bit more, we're going to evaluate our first polynomial with its 2 data points, so x1 and x2. P2 will be evaluated at x2 and x3, and lastly, P3 will be evaluated at x3 and x4. As you can see here, this results in 6 of our 12 equations. Secondly, again as we learned in the cubic spline interpolation theory video, we can find n-1 equations through the property of smoothness at our interior data points through equating our first derivatives, which in this example will give us 2 more equations as we have 2 interior data points. So, we simply find the derivatives of our polynomials with touching interior data points, and then evaluate them at that input. And here are the 2 equations that we get from this. Likewise, we can find n-1 equations from doing the same thing with our second derivatives. As in cubic spline interpolation, we have smoothness at both the first and second derivatives. Then we are going to equate them and plug in our x values just like we did earlier. And here it is x equals 3. This works out to the following equation, and I'm just going to rearrange it such that all variables are on one side and the constant on the other side of the equation. Secondly, we'll repeat this process for our second interior data point between P2 and P3. Therefore, we will again take the derivative of our first derivative, p2 and p3 functions we found earlier, and evaluate them at x equals x3, which is 5. And again, just rearranging and putting everything to one side, and it results in this equation. Now, as you can see, we have 10 equations and are only missing 2. As we were told earlier to use clamped cubic spline, and our instantaneous rate of slope at both endpoints is 4, we're going to use that now. In a clamped cubic spline, we'll use some known facts about the rate of change at the endpoints of our interpolating function. As we were told in the beginning of our question, assume that the rate of change at points x1 and x4 are 4. So let's just go ahead and use our previously calculated first derivative of p1 and p3 at points x1 and x4 respectively to get our remaining 2 equations. Now that we have all of our 12 equations, we can fully solve for our 12 unknowns. To do this, we could try doing it manually. However, this would not be fun. Through using simple polynomials, we will always have linear equations, and therefore a system of linear equations. We can use our linear system of equation solvers that we have developed in the past. So let's just write out our matrix so that we know what we are going to be trying to solve for. You can think of these columns as our coefficient values for each of our equations. And I will write this out like so it's easier to visualize. Now, I'm going to use our Gauss elimination solver with partial pivoting that we developed in a previous numerical methods video. I will leave a link to that video down in the description down below if you missed it. However, there are also a system of linear equation solvers online that you could find by Googling them. Now that we're inside Python, I have opened the Gauss elimination system of equation solver with partial pivoting. I took a minute already and entered our square matrix we just wrote down and entered it into our variable and constant matrices here. Now, we just need to call our function and insert our variable matrix and then our constant matrix and run the program. As you can see, we have now solved for all of our 12 unknowns. Each of these x values represents a coefficient for our 3 interpolating polynomials. x0 is a1, x1 is b1, x2 is c1, x3 is d1, and so on. To visualize these polynomials, I'm just going to plot them rather crudely inside Microsoft Excel, keeping in mind our domains that we talked about previously. As you can see, this results in the very nice smooth function. In the previous video, we were asked to interpolate over the same set of data as we did in this video. However, in that video, we were using a natural cubic spline, whereas in this video, I wanted to use a rather extreme example of a clamped cubic spline to show you how they vary visually. As you can see in the clamped cubic spline example, since we set the first derivatives at the beginning and end rather steep at 4, the polynomial functions need to contort themselves to achieve the smoothness and continuity throughout the length of the interpolating polynomial. Hi everyone. In the past few videos, we have been talking about spline interpolation, and the varying degree of complexity we can add to improve our interpolation results. In particular, we are going to now talk about how we can implement these 3 spline interpolation methods that we've been talking about in the past couple videos into Python, those being linear splines, quadratic splines, and cubic splines. To demonstrate spline interpolation, let's begin with a simple dataset. Here we have a list of x and y values representing some points on a graph. To do this, we are first going to import all of our necessary Python libraries. These libraries are going to be matplotlib, scipy, and numpy. To import these libraries into PyCharm, which is the IDE that I'm using in this video, we're going to click on our interpreter in the bottom right corner of our screen, and then click Interpreter Settings. Making sure you have the correct interpreter selected at the top here, we can now go down to this plus sign at the bottom of our window. This button is going to add packages to our Python interpreter. So, within this window, we are just going to search for all 3 required packages and add them to our interpreter so that we can begin playing with splines within Python. Now, back to our main Python file, we can import our downloaded packages. Then, let's just go ahead and create a simple 1D array of values that we want to interpolate. In our linear interpolation example, we use this set of data, so I'm just going to reuse this now. To visualize our data, we are going to use matplotlib. To begin, let's just create a simple scatter plot of our data. To do this, let's call our matplotlib function like so, and tell it we want to plot our x and y data points. Now, if we run our file, it'll give us a line graph, but that's not what we want right now. We said that we wanted to plot a scatter plot. To do this, we just add a circle marker to our data points like so, with a label to denote it that these are our data points. Lastly, I'm just going to add a legend to our plot like so. Now, when we run the program again, we can see that we have just created our scatter plot, which is exactly what we wanted. To create a linear interpolation between these data points, we need to create two variables. Firstly, we need to create another set of x data points that will be plotted along with our interpolated y values. One way of doing this is through the NumPy linspace function, which takes a starting value, an ending value, and then a number of equally spaced intervals between those two previous values. As we can only interpolate between our lowest x value and our highest x value, I'm going to use the NumPy min and max function such that our xInterp variable fluctuates with our data entry. Then, let's just arbitrarily select 50 intervals. Now, let's make a one-dimensional linear spline interpolation through these data points. To do this, we'll make a new variable called yLinear. Then we'll call our 1D SciPy interpolation function like so, and tell it that we want to interpolate our dataset. Now, let's just add in another plot like so. And we'll give it a color, so let's make it red. Lastly, we'll just add a label denoting it as our linear interpolation. Running our file again, we can see that we have now interpolated our data with linear splines. Just briefly, if you wish to use the interpolating function to find the output of any given input along your domain, all you need to do is call our yLinear variable and give it an input like so. Running the file, you can see that we are printed the output. This allows you to easily call the function and use it however you need. Much the same way, we can implement one-dimensional interpolation using quadratics and cubics. Let's first show how to do this with quadratics. Let's make a new variable called yQuadratic. Then we will just copy our linear code from earlier, and all we need to do here is add a statement of kind at the end. Tell SciPy that we want our kind of interpolating function to be quadratic in nature. Then, we add another plot like we just did for the linear interpolation. Running our program, you can now see that we have successfully implemented a quadratic interpolation. One thing to note here is if we do not have enough intervals in our x direction on xInterp, then our quadratic spline will not look smooth. This does not change anything about the yQuadratic object, it's just visually how matplotlib can interpret and present the data to you. Lastly, let's talk about cubics, the most common form of interpolation. I'm just going to go through the exact same process that we just did with the quadratic splines. We'll add a new variable called yCubic and set our kind to cubic. Then we'll add another plot like we did with the past two interpolation methods. Running our program, you can now see that we have successfully implemented a cubic interpolation. One thing to note here though is that we cannot manipulate boundary conditions through this method. We will need to use something like the cubic spline function. So let's show how that works now. Let's add that function to our import. Then I'm going to call the cubic spline function and add a boundary condition of natural, as we learned about in our previous cubic spline interpolation theory video. Then we'll add the plot line of code and call it cubic spline BC for boundary condition. After we run this file, you can see that the cubic spline seems to fit much more appropriately using this natural boundary condition. I hope that this video helped your understanding of how you can implement and use one-dimensional spline interpolation within Python. If you enjoyed, please like, subscribe, and consider checking out our YouTube memberships by clicking that join button down below. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.